docente investigador del Instituto de Ciencias de Materiales de Madrid. Él obtuvo su doctorado en el 2009 bajo la supervisión de la profesora Ángeles Monge y la doctora Natalia Snesco. Y después se fue a una estadía postdoctoral bajo la supervisión de Omar Yaghi en la Universidad de California. Y después en California, Los Ángeles, y después en California, Berkeley. En 2014 volvió a Madrid y se unió al Instituto de Ciencias de Materiales y obtuvo en el 2017 una beca Ramón y Cajal. Y después obtuvo una puesto fijo. Durante su carrera publicó 75 artículos y participó en 17 proyectos, 5 de ellos como investigador principal, combinando estudios estructurales y sintéticos. Sus intereses actuales de investigación están enfocados en el mejoramiento de las propiedades de los materiales reticulares para lograr más altos niveles de complejidad a través de la elección inteligente de los constituyentes químicos. Now, in English, Felipe is currently a staff scientist at the Material Science Institute of Madrid. He obtained his PhD in 2009 under the supervision of Professor Ángeles Monge and Dr. Natalia Espejo, and then became a postdoctoral researcher under the supervision of Professor Omar Yaghi between 2009 and 2014. First at the University of California, Los Angeles, and then at the University of California, Berkeley. Okay, I think that Felipe will talk enough. Will give us a very nice chat. Bienvenido, Felipe, gracias por estar con nosotros.
Muchas gracias.
La audiencia a tu servida.
Gracias por la presentación. Thank you very much for your introduction. I'd like to thank you and the organizers for inviting me today to present some of the results of our group. It's a pleasure. It's even a greater pleasure when this in the organizing committee there are really good friends of mine, like in this case. I'm really happy to have had the chance to work together with Celeste and Alejandro and at different stages of my career. And so I'm trying to share my screen while I am talking. So let me just make sure that it is working now. So hopefully it's now sharing the screen. Perfect. Okay. So I was saying that thank you for the invitation and thank you for all the organizers, especially Alejandro and Celeste. They are a really good friend of mine. I had the chance to work together at different stages while I was a PhD and also as a postdoc, and I know very well how really good scientists both of them are, and all the hard work that they are doing in and I think that it was a great initiative also to have this symposium, Argentina symposium on meta-organic framework. I'm well aware that the field is growing. It's growing everywhere. It has been growing for many years, but I know it's growing also there in Argentina. So it's really great to have this symposium put together. So congratulations on the organization, to all the organizing committee. So this being said, I'm going to start with the presentation. I'm talking today on one of the research lines that the group is carrying out. It's actually a quite mature research line. It's one of the first one that was initiated in the group regarding meta-organic frameworks. It's related to the use of MOFs for in catalytic application in heterogeneous catalysis, but also and the key point here is that is focus on building MOFs, synthesizing MOFs from metal elements that are from the main group, from the main groups in the periodic table, particularly for the P-blocks element. I will show you in a minute. So one of the most beautiful parts of MOF chemistry, from my point of view, is really that you can basically have any element you want, incorporate it into a crystal structure, and we have the whole periodic table of elements to combine metals along with the organic linkers. But I always have considered myself more an inorganic chemist rather than an organic chemist. Despite now I am a MOF chemist. MOF reticular chemistry is also a field of chemistry for what it takes. So nevertheless, having the chance to combine any element, any metal element that you can think of, I think is one of the most beautiful part. And because with this you can really modulate, change the properties of the materials to a greater extent. We just saw in the previous presentation with the small changes in the metal elements in the lanthanide that are selected, how the properties and the physical properties and the application of the MOFs can be tuned and changed. Nonetheless, most of the MOFs have been made really with transition metal elements, and particularly the first row metal elements are the most abundant. There is no doubt. And there are so many secondary building units that you can combine and you can form with this metal element and get different structures. But there are not so many of all the materials made of MOF materials made with P block elements. And so if we focus on the P block metal elements, there are not so many possibilities. So actually, if we don't consider, of course, any of these transuranic elements and radioactive elements, and we also don't consider thallium, lead that are highly toxic, and we avoid them, we basically end up having aluminum, gallium, and indium, and then also bismuth. Tin coordination chemistry is quite different from the other elements. So I don't think there are many examples of tin compounds that can be coordinated, for example, to carboxylic acid groups that are most abundant in MOF chemistry. But that is not the case for aluminum, gallium, and indium, as well as bismuth. So the first three ones, aluminum, gallium, and indium, actually they are way more similar to transition metal elements. They are trivalent, that they can have very similar coordination environments and behave in a similar way to transition metal elements, while bismuth is kind of different. It has also a very rich and interesting coordination chemistry, and I will show some examples today of bismuth MOFs and many differences, some of the differences that you can see in the way that it behaves when mixed together with organic linkers. Nonetheless, there are some famous examples, some rockstar MOFs that have been synthesized over the years with some of these elements, like the SOC indium MOFs by Raudi's group, the famous MIL53, that it was first reported with chromium, but then shortly after with aluminum, and all the derivatives that came with this with these isoreticular versions of MIL53 with different organic ligands, longer or shorter linkers. Other aluminum MOFs include MOF520, and there are already some interesting examples with bismuth, like Cow7. I don't think it's the first bismuth MOF, but it's definitely one of the. It's among the first bismuth-based MOF that was reported, and it was it was a quite nice structure. If you have had the chance to see this, how the hexagonal pores of these MOFs are formed with rod-shaped SBU. So regarding indium MOFs, as I was anticipating before, this is one of the research lines that was first initiated at the Material Science Institute of Madrid a few years ago already. So indium PF1 on the left is the first indium MOF that was actually reported in the literature. It was down back in 2002. So I was an undergraduate student by that time. I didn't have any idea what a MOF is, or my interests were really put in something else, not even science, when I was in undergraduate school. But very exciting chemistry was already happening with regarding MOFs and also with indium MOFs. There were already very cool examples like this one. And when I was already doing my PhD, I had the chance to investigate in this line, in this research line, and have some examples of indium MOFs that were quite robust. This particular example was also porous, and it had really good catalytic activity. By that time, we were basically testing the catalytic activity of these MOFs as Lewis acid catalyst, and proving that the accessibility to the indium metal center was quite helpful to get reactions that are catalyzed by acid like Lewis acids. For example, the acetalization of benzaldehyde, which is a standard test reaction to demonstrate this Lewis acid character of the material. So more recently, we have continued with this line, with this research interest, and recently we published this review where we were looking at most of the MOFs that were synthesized with aluminum, gallium, and indium with blue 13 MOFs with 13 element. And this is data from 2017, so there have been more new MOFs ever since, but that was quite illustrating of the abundance of these materials compared, for example, to transition metal elements, and you can see that they account for less than 5% of the total number of MOFs that are available in the literature and in the databases. Most of them are aluminum. There is just 1% of indium MOFs, but they are very interesting, and just a small portion of gallium MOFs. I'm not showing any gallium MOF today, really, but we have some beautiful examples of gallium MOF that can be synthesized also with this element. Looking at them, one of the most important parts in the MOF from the structural point of view is, of course, which are the secondary building units that you can make with these elements, and then you find that you find some all known secondary building units. For example, this trimeric SBU that is also known for other trivalent metal elements, one-dimensional change with octahedral, for example, octahedrally coordinated atoms with sharing vertices, but there are also some other dimeric SBUs were also identified, a lot of monomeric secondary building units, and other aggregates more or less complicated with a higher number of metal elements. So in indium MOFs, among all these secondary building units, it turns out that monomeric secondary building units, meaning those that have only one metal atom in the coordination, sorry, in the secondary building unit, are the most abundant. There are also small clusters, dimeric and trimeric, but if you consider trimeric and monomeric SBU, as well as this rod-shaped one-dimensional SBU, you have more than 90% of the indium MOF. So these are the three major SBUs that you usually see when you are synthesizing MOFs, at least with the synthetic conditions that are most usually reported. It doesn't mean that we cannot get other coordinations or other SBUs, but definitely with the most extended synthetic conditions, these are the ones that you most of the time find. The coordination environment of indium, if in comparison with first row transition metal, is also different. It very usually 6-coordinated octahedral, but there are also a number of 8-coordinated indium MOFs as well as 7-coordinated. So it's a little bit more flexible in terms of the ability to have a larger number of atoms surrounding the coordination environment, and it's kind of richer compared to transition metal or first row transition metal. And finally, just mentioning that the periodicity of most of them are three-dimensional structures, three-dimensional networks. Despite that, you can also synthesize 2D or two periodic MOFs. So one of these examples of indium MOFs that we have reported in the lab is indium PF 110. By the way, PF stands just for a polymeric framework. That was a nomenclature that we adapted from the very beginning, and we still stick to it. And we just have the metal element at the beginning of the name of the MOF. So this is a mesoporous structure. as you can see, not only from the crystal structure, but also from the sorption isotherm with the typical step at the relative pressure once you get condensation into the mesopore. It's nearly 3 nanometers aperture and has hexagonal channels. It's hexagonal crystal structure, by the way. And from the structural point of view, you see again one of these trimeric secondary building units. So the oxocenter trimeric secondary building unit that is known with indium, and when you combine it with BDB, which is also a very versatile organic linker for making MOF, produces this beautiful structure with a large number actually of accessible indium sites pointing into these large hexagonal pores. There are also some smaller pores that are accessible through these small windows here, but most of the absorption can happen into these larger pores. From a topological point of view, but we always also like to complete this topological analysis of the MOFs, because basically it's how you really get to put order, a little bit of order in this large amount of MOFs that are accessible in the literature. So it's how you can classify MOFs and compare with other similar structures. So from the topological point of view, indium P110 is simplified by having this inorganic SBU as a trigonal prism combined with triangles, and then if you get these two secondary building units, you can form this type of network that actually was reported before we published this paper with the use of scandium. It's a similar in this topology. However, there were differences in terms of in structural terms, because what is happening actually here in this structure is that the secondary building units are directly linked by presence of formate anions. These formate anions were not introduced in the synthesis, but they were formed by the composition of the DMF solvent. This is quite common, particularly also when you are using elements like indium or aluminum that are indeed Lewis acids. They can also promote the decomposition of DMF and the formation of formate anions that are actually linking these secondary building units. If you consider that this is an extended secondary SBU, the topology of the structure is different to the one that I just depicted. Anyways, considering that this is a highly porous MOF with a large pore aperture, we were at that time interested in the development of MOFs for as catalysts for multi-component reaction. In multi-component reactions, basically you have various substrates, and when you carry out this reaction in one pot, basically you put together all the three of them with the hope that you will get the desired product. But of course, there could be other byproduct, there could be other side reaction if you have everything together. So we need catalysts that can be active but also selective to the formation of the desired product. In the particular case of the structural reaction, the desired product is this alpha aminonitrile, but you can also that is produced when you react carbonyl, amine, and a cyano group coming from the trimethylsilyl cyanide. And but it could be happening actually that there is also the cyanolylation product when the amine is not involved, or that you get the imine formation and the amine formation between the carbonyl and the amine. But in this case, we found that the catalyst is highly active and is very selective to the formation of the alpha aminonitrile. And it was actually made with ketones. You can do the structural reaction with aldehyde or ketones, and ketones usually are more difficult to activate compared to aldehydes. But in this case, the MOF was very active. You could see that in very short period of time, in a few hours, you get 99% yield and close to quantitative conversion of the reactant. This the proposed mechanism for this reaction, basically you need presence of different type of active sites, and most importantly, you need to have a kind of synchronization regarding the formation of the intermediate product and presence of the other of the substrate. For example, in this case, basically you need to have Lewis acid sites that can catalyze the formation of an imine intermediate, but at the same time, it has to be in the vicinity and nearby the trimethylsilicyanide that has to be also activated near the formation of this imine and to produce the alpha-aminonitrile. Otherwise, you could have this other byproduct or side reaction we believe this happening actually with this MOF. And moreover, we could get actually some crystallographic evidence or support for this, because what we found is that when you swap this material with aniline, in presence of aniline, as well as the other substrate, we could isolate a crystal where we found that the aniline is actually getting coordinated to the secondary building unit. One of the positions in the coordination environment of the indium atom is occupied by a water ligand that is incorporated during the synthesis of the material, but is partially replacing this water ligand. This is 0.5% of occupancy for the red oxygen and the green nitrogen atom from the aniline. It's partly replacing, so we have it. We have the aniline in the vicinity of the secondary building unit, having favoring the formation of the mean intermediate, and then the trimethylsilicyanide will be also activated by this view and then attack this imine group. So that's why we think is the reason behind this very high activity, at least in this particular example. Now, while we were studying this system, combining indium and BDB, we actually isolated two other MOF type of MOF crystals, two different crystals that in both cases, I will show you in the next slide, they correspond to two periodic honeycomb type structure. So remember I was saying most of the indium MOF are actually monomeric, and this will be the case for this. But we also found that there were differences depending on which was the initial choice of metal salt. When you use indium chloride, we will get indium PF51 and indium PF50. It's very similar, but it's structurally slightly different. Crystallographically is completely different. Was obtained with fluorine, with nitrates, and also with acetate. So by tuning the synthetic conditions and optimizing the synthetic conditions, we could isolate as pure phase both crystal, and the crystal structure for both of them is as follows. So in both cases, we get these monomeric secondary building units, as I was saying. Now each indium atom is coordinated only to three carboxylic groups, and in this case with an additional water ligand, forming a two periodic structure, honeycomb. But it's not just a single layer, but rather we have a pairs of catenated layers. So this is the top view, and this will be the side view for the pairs of catenated layers. Here you can see how the orange and blue, they go up and down alternately doing this catenation. In this case, and this was also what was happening in indium PF51. But you can see now that the way the layers are disposed is slightly different. So but in both cases, you see that these are wave-like layers, or they are not perfectly flat, but the way that they propagate is different. Another important difference in this case is that, first of all, well, crystallographically are completely different, and they have different space group and different symmetry. And also there is presence of chlorine atoms in indium PF51. So each indium atom is coordinated to three carboxylic groups, but then it's also this chlorine atom, and it's producing a negative charge of the layers. And then here there is presence of counteranions that are dimethylammonium cations that actually are again formed by the decomposition of the DMA. They were not added during the synthesis, but they were actually produced during the decomposition. So just a quick comparison of both materials. You see that, as I was mentioning, they are wave-like two periodic structures, but the amplitude, how this wave propagate, is different. In one case, they are closer to this flat position or flat disposition in indium PF51, while in indium PF50s it's a different angle. It's a shorter angle, close to 90 degrees actually. We tested them also in multi-component reaction. In this case, we were studying the Yugi multi-component reaction. Now we have 4 substrate that has to be put together in one step. And we will also comparing with the MOF110 to see the differences in the between the different type of SBUs. Now these are not so porous structures. So in this case, the catalytic activity must be taking place on the external surface. There is no such a big pore here, at least in 50 and 51, to allow the diffusion of all the 4 substrate. But nonetheless, despite the number of accessible sites is probably smaller as compared to 110, we found that they are more active. And in both cases with low catalyst loading, 0.5% mole percent, this is per atomic percent per Indian atom, you get very high yield values and high turnover numbers. So you see here with, you could do the reaction solvent-free or with ethanol. The conversion was higher with ethanol because basically the product has to be solubilized as a solid, so it's better to have some solvent, even if it is ethanol, to facilitate the catalytic reaction. So in this case, again, we need presence of a couple of different active sites. On one hand, we have the Lewis acid sites, but on the other hand, we need Lewis base sites for the reaction to take place. And one difference here is that there are some of the oxygen atoms from the carboxylic groups that can actually be, let us say, open or separated from the Indian atom when there is presence of the substrate, and they may act as a Lewis basic sites and favoring here this the reaction. In the case of Indian PF51, which was the one with the highest yield values, we also studied, of course, this the scope of the reaction, and we found that it's very active with different type of aldehydes, not with all of them. For example, with alkyl change aldehydes or amines, the activity of the material was not sufficient, and we didn't see any problem. So one more comparative example, because I bring it because also related to the previous one, to this type of material, is this other series of MOFs. I'm talking only today here about this Indian one, the particular MOF A94. This was in a collaboration with Vietnam National University group, Inomar group, and Hong. She was a grad student that she spent some time in our lab in Madrid and synthesized some of these MOF materials with in this case the hexaphenyl hexabenzoic organic linker, and with zirconium, but also with indium. They had prepared already the zirconium versions in Vietnam, and prepared this new indium MOF here in Madrid, and it's very similar compared to the previous example of indium PF50 and 51 in the sense that, again, we find monomeric secondary building units and layer structure. Now, instead of triangles, we have this hexagonal linker, so that the topology of the layers has to be different. We cannot have this catenation anymore. These are Kagome dual networks of layers, and here there is no catenation possibility. But in terms of the chemical composition of the SBU, you see that again we have monomeric SBUs, and in one of them there are 2 crystallographically independent Indian atoms. In one of them, actually, there is additional acetate anions coordinated, again providing a negative charge to the framework. In this case, this was acetic acid was added as a modulant during the reaction, and they were coordinated. And again, there was presence of the dimethyl ammonium cations to compensate the charge. So in this case, the reaction that we were investigating at that point was the insertion of carbon dioxide into styrene oxide. Later on, we also investigated directly on alkene, but in that work we started with the oxide already preformed, and the material, despite they were not very porous, but they had some porosity and absorption capacity to carbon dioxide, not to nitrogen, but it had higher affinity to carbon dioxide, and it was providing a very good conversion, very low temperature, only 1 atmosphere as a carbon dioxide balloon, and high selectivity and mild temperatures compared with other catalysts. So moving on, we are now investigating the possibility to use other metal elements instead of indium that could have similar or comparable catalytic properties, but they have, in this case, we are using bismuth because it's more abundant than indium, it's less expensive, of course. It's also a non-toxic element. Bismuth has actually a lot of potential in MOF chemistry, despite its coordination chemistry is really rich. It's a very interesting element because the coordination number of bismuth can go from low coordination number of, for example, 6 up to 9 or even 10. Sometimes bismuth is found replacing rare earth elements, so it's similar to rare earth elements in for example, in oxides and in other compounds. But in MOF chemistry, there are already several examples reported with bismuth, and we are trying to understand how it behaves under similar conditions as, for example, with indium. In this case, we are investigating the system by combining indium and bismuth with this methyl tribenzoic acid linker. It has a tetrahedral shape, and we combined it with indium and bismuth and synthesized at least 3 different MOFs. Where 2 of them, indium PF60 and bismuth PF5, actually are isoreticular. They have basically the same formula with the substitution of indium by bismuth in one case compared to the other. And then another one, bismuth PF7. I show you the structure. This is, by the way, unpublished results. We have a manuscript in preparation, but these are really cool. I really like these structures, so I wanted to show them with you. When you compare this indium PF60 and bismuth PF5, I was just telling you, they are isoreticular. They have the same type of network. The SBU is it's different. They have different metal elements, but in topological terms, they are equivalent because we have just one metal element coordinated to four carboxylic groups. In the case of indium, the coordination number is 7 because one of the oxygen atoms is actually that's a distance that is farther from what you would expect for a coordination bond. It's a little bit longer. In the case of bismuth, it has a larger coordination sphere. The coordination number is actually 9. You have all the 8 carboxylic oxygen atoms, as well as one water molecule. But again, these 2 MOF, they have the same type of structure. They are isoreticular. They form diamond type of structure, actually 2 diamond catenated networks, because we have in both cases a pair of catenated diamond networks. The secondary, the inorganic SBUs, they act as tetrahedral nodes, as well as the tetrahedral organic linker, and then we produce this beautiful diamond type of structure, and they provide a very good opportunity to compare the activity of the material with in similar conditions, because other than the nature of the metal, we have very similar environment in terms of pores and everything. By the way, these are also anionic structures. You will probably notice already that each indium atom is coordinated to 4 carboxylic groups. That's the overall network charge is negative. So the third in question, the third MOF here, is bismuth PF7. It has a completely different structure, the same building constituents, bismuth and this the same methyl tetrabenzoic ligand, but now we have 2 different types of SBUs, very highly related, but chemically different. Both of them are dimeric with 2 bismuth atoms coordinated to 6 carboxylic groups. These are neutral SBUs, but now in one case we have just 2 apical water ligands. In this case, we have 3 bridging oxygen oxygen from 3 water ligand bridging these 2 the 2 metal centers. Then when you look at this at the 3-dimensional structure, this is a rhombohedral crystal structure. It shows this beautiful type of framework. Here is this is a view from the z-axis, from the rhombohedral axis, and then you can see that it is formed this kind of, I don't really know which is the correct name for the shape. It's kind of a star shape, right? If you look it from the top. But basically you have here a if you look at it and rotate it, is like there is formation of cages that are sharing vertices, and actually there are pairs of cages that are also catenated. Again, here this is a simplified view where we have the inorganic SVU simplified as trigonal prisms, and then the organic linker as a distoric tetrahedron, and then there are pairs of catenated cages that actually propagate along the z-axis. Now, what is beautiful here is that when you see the three-dimensional structure, actually these pairs of catenated cages that are fused together, they actually get to connect. If when you go with two of these, let's see here with the color scheme, this is the same view as before, but now you can see that blue and red, they have independent network. They are catenated, but they are not forming bonds between them. But when you go from one of these to another two of them, at some point the blue and the red, they meet together and they form just one network, which is called a self-catenated type of network. So anyways, besides this structural beauty of the MOFs, we already performed this catalytic activity test again in the Strecker reaction. In the case of indium PF60, we were expecting to have a high activity to the Strecker product, again the alpha amino nitrile. The nitrile product, very high selectivity, up to 9 cycles. Have been used in 9 consecutive cycles, 99% of selectivity and more than 95% on conversion. However, with the equivalent bismuth version, bismuth PF5, what you get is actually the cyanocylation product with a 99% of selectivity. You don't get to produce the alpha amino nitrile, but rather what you have is that the ketone and the trimethylsilyl cyanide are reacting really fast, too fast as to allow the formation of imine intermediate and then proceed to the alpha amino nitrile. In the case of bismuth PF7, a different type of secondary building unit, we can obtain actually good selectivity again to up to 99%. Only in the ninth cycle, the selectivity decreases slightly, but very high values of conversion. So it's really a good opportunity here to compare and to get a little bit more of insight into the role of the metal center and the metal coordination environment into the overall catalytic activity of the MOFs, comparing indium, bismuth, and different topologies. So the last example I'm going to show today is photoelectrocatalytic active MOFs, again made out with bismuth, but bismuth here really is not, as we found, is not playing any role on the catalytic activity, as that we could find for the photoelectrocatalytic mechanism. So the material was synthesized again, starting with bismuth nitrate, but then with a linker that was designed, selected because it's made of fused thiophene rings. And then this kind of linker can behave as a whole transport linker, and which is useful for photoelectrocatalytic applications. So this dithienothiophene dicarboxylic acid, TDC. So this linker was synthesized in the lab. This is a collaboration with the group of Victor de la Peña at Indea Energy. So that was synthesized in the lab, and the MOF was made out with this linker. From the structural point of view, we see a different SVU again. This is a bismuth 3 SVU, trimeric SVU, but now it's just this trimetal element, trimetal atoms, but linearly disposed. It's not like this, the previous trimeric SVU that we showed before. And once they are coordinated to, each one of them is coordinated to 12 carboxylic groups from organic linkers. They are forming these pillars with 2 linkers to form primitive cubic PCU networks with, again, pairs of interpenetrated networks in the overall framework. Again, this is an anionic. Now it's an anionic MOF, and there is presence of dimethyl ammonium cations that were again formed during the MOF synthesis reaction because we were using DMF as the solvent. So this was tested in the photoelectrocatalytic hydrogen production. We made a film deposited of IDO slide and deposited the MOF. It was denoted IEF5 because it was first synthesized in the Energy Institute with I just say with Victor de la Peña in his lab. And then what we tried is we tested it as a photoelectrocatalyst for hydrogen production. And we found that indeed there was some hydrogen evolution. After hour and a half, we detected the hydrogen with application of a bias voltage as well as with the light. So interestingly here, there is no other metal element in the catalyst. This is used as a photoanode by itself, just the MOF, nothing else here, and this is the working cell under the visible light. So we did a study of charge dynamics to investigate more what is going on with what is the possible mechanism. So we did this study first. Not shown here with core clock experiments in the synchrotron that they were used to investigate the first stages in the process, which is the charge separation, and that was telling us that it's actually happening in this thanks to the presence of the thiophene fused thiophene linker, and then after that with this laser flash photolysis experiment. We found that there is a formation of a band at 440 nanometers that was assigned to a formation of excited state of the MOF, and that was assigned as a triplet because when there was presence of oxygen of air that are known to quench triplets, then you can see that the intensity of the band decreases significantly. So that's why it was assigned. Then when we study the presence of electron donor molecules, we found that with presence of sulfides that were used in the reaction, there is a quenching on this initial band at 440 nanometer signal, and then there is the appearance of a new band. And that observation was attributed to the transfer of the electron from the sulfide to the MOF excited states, thus quenching this band and the formation of a new one, these new transient bands. It was observed 515 nanometer, and there is a big difference in the lifetime compared one to the other. And then for this, what we assign is that this to the formation of a new radical anion species of the MOF, thanks to the presence of the sulfide as electron donor that was used in the sodium sulfide, was also used in the photoelectrocatalytic reaction. With this, we could actually propose a mechanism of what is going on when you shed light to the MOF. The MOF is in the anode, is illuminated with visible light, and then what is happening is that first you have a charge separation, and then you generate a state. A state that is goes through a intersystem crossing, goes to a triplet excited state. And this was also supported, by the way, with DFT calculations, as well as with this series of experiments. And then when you have the sulfides in present, they interact with this the holes generated in the MOF, and they inject charge into the framework. So then what is happening is that a radical anion is formed. This can go from the singlet or from the triplet excited state, actually, but most likely is happening from the triplet. And then the radical anion is the active species that then interact with the platinum cation. It gives the electron to produce hydrogen, and then the cycle is again closed. So it was actually a very cool work, a paper where we got a lot of information from the structural point of view, from the synthesis of the material, as well as from these time-resolved experiments that gave a lot of information on how the process is happening, and the important role here of the organic linker. We didn't see any influence of the metal element. So I just finished. So this is that was actually my last slide. I just thanking everybody and at the multifunctional supramolecular materials group here at ICMN, particularly at current former members that were or are still involved in this research line related to indium and bismuth. Ángeles Monge, Enrique Gutiérrez is still active, as well as Marta Iglesias, with whom we are carrying a lot of these catalytic studies for multi-component reaction. Natalia Snoiko, she got retired a few years ago already. Now she's a full-time grandma, but she was the first person actually synthesizing these indium MOFs in the world. And that was opening a brand new research line. And as you can see now, many beautiful examples of materials have been synthesized thanks that somebody at the beginning opened this research line. Lina, she worked a lot also on indium MOFs, as well as Daniel Reinares. He was a PhD student. His thesis was focused on indium MOFs, and Eloy, a master student who has been working on bismuth and some of these indium materials. Just already mentioned Victor de la Peña, of course, a long-time collaborator and friend of mine, and Alba Garcia, the student who's finishing her PhD on these photocatalytically active materials. And I also showed today some examples of the collaborative work with BNU, with National University, in particular for this indium MOF894. So that was everything I had today. So thank you very much for your attention.
Gracias, Felipe. Fue muy interesante la charla. No solo con video porque tengo un problemita con la cámara. Pero nos quedó tiempo para una preguntita que Alejandro Fracaroli. Thank you, Felipe. Great talk. Just wondering if you have considered purging an anti-selectivity using indium PF110 or other indium MOF catalyst for the Strecker reactions.
Yes, so not particularly for indium PF110, we have not considered it because it's actually a centrosymmetric crystal structure. There was not really any, if I recall, I think I'm right, but there is no any chiral center there, but there are other MOFs really where you could crystallize them with chiral space group. In that case, it could be interesting, but we haven't done it so far. We haven't done it. Although I know Strecker and also the UGI reaction, they are very interesting and very important for if you can get some anti-selective products.
Bueno, gracias. Hay un montón de preguntas más, pero les voy a pedir que te las manden, porque si no se nos atrasa un montón el resto de las conferencias. Gracias de nuevo.
De acuerdo.
Felipe, muy amable.
Muy bien, muchas gracias.
Bueno, y ahora, siguiendo con las charlas, ahora va a hablar Javier Fur,